Okay, students, so let's go ahead and let's do the next part of this. So we're going to look at tangent and cotangent graphs, and I tend to do tangent and cotangent a little different than I do the other graphs, so I'll kind of show you a little bit different technique that I tend to use on this. Mostly it has to do with locating asymptotes, and to begin with, we're going to look at just the basic graph. So you got to remember what you do on a tangent. A tangent is y over x. Oh, come on, pen, work. There we go. Okay, so a tangent's y over x. Okay, so yeah, we're going to do y over x all the way around the unit circle. Okay, so to begin with, let's just start kind of on the unit circle. I'll just kind of write down what we have. At 0, y over x would be 0 over 1. So therefore, the tangent is 0. We go to pi over 4. Y over x would be root 2 over 2 divided by itself. So that would be 1. If you go to pi over 2, y over x would be 1 over 0. So that's undefined. So you're going to have a vertical asymptote there. 3 pi over 4, you can pretty well do that in your head. That's y over x is going to be negative 1. And then finally at pi, y over x will be 0 over negative 1 back to 0. So that actually gives you a period of a tangent from 0 to pi. If we go backwards through this, the same logic, if you go to negative pi over 4, y over x is negative 1. If you go to negative pi over 2, y over x is undefined. And then negative 3 pi over 4, you go that way, you would have 1 again. And then halfway around the circle would be y over x would be 0 again, like that. So those are your key points. That's coming from doing y over x, okay? So let's go ahead, let's get this put together. I'm going with a different increment on this for a reason that we'll see in a minute. So we want to just get everything set up. We got pi over 4, pi over 2, 3 pi over 4, and so forth, all the way up to pi. You want to do the negatives, same way. Okay, so let's just get everything set up for plotting points, then we'll talk about the meaning behind what this table of values is doing. Okay, I'm going to recommend we go up to not 1, but to 4 or 5. Let's just go up to 4 and then maybe down to negative 4 like that, and then we're just going to focus on plotting points. So what happens on a tangent graph is we're undefined at certain places. One place is pi over 2, so we're going to end up having a vertical asymptote that goes there, just kind of like we had on the secant and cosecant. Also at negative pi over 2, you want to sketch out a vertical asymptote there. And then the rest of this, we're just going to plot points. So at negative pi, the y value is 0. At negative 3 pi over 4, I'm going to go up 1. And what happens is the graph is going to kind of do this kind of thing. We're going to go through these points, but as we get close to that asymptote, we're going to turn towards infinity like that. Okay, and then if we do the rest of these, let's see, negative pi over 4, we're down at negative 1. We have a point 0, 0, pi over 4, 1. And then again, the graph is going to do this kind of thing. It'll approach the asymptote from the left going to infinity, and it'll approach the asymptote from the right going to negative infinity. And then the rest of it's pretty similar. 3 pi over 4, negative 1's a point, 0, 0's a point, and then you just sketch. So really, these are kind of the key points on the tangent. And again, I want to show you on my calculator kind of what's going on this. And it's real helpful to understand asymptotes. So I'm going to, just for simplicity, I think just for demonstration, I'm going to put my calculator in degree mode. And you just need to watch this. What happens is pi over 2 is 90 degrees. So if I was to do the tangent of something real close to 90 degrees, say like 89 degrees, something on the left, well, you get a fairly big number, see. And if I go tangent of something even closer, like 89.9 degrees, Well, I get bigger and bigger. So the closer you get to that asymptote on the left side, the higher that number becomes. And by the same process, if I went tangent of 91, something a little bigger than 90, notice I'm getting into negative numbers. And if I did something like tangent of, say, 90.01, well, that's real close to 90, but to the right, look what happens. I get a real small number, so that kind of shows you what's going on there. Technically, what you're doing is you're dividing by a number that's real close to 0 around a vertical asymptote. So it either goes to infinity or negative infinity. So that's what your graph looks like, kind of your key points. I kind of look at a period kind of like this. On a tangent, you have an asymptote, you have a y value of -1, y value of 0, y value of +1, and then another asymptote. That kind of gives you the key points right there. So the period is going to be pi this time. Okay, so again, the distance on that, when you're doing the period, you're going to do pi over 2 minus negative pi over 2. So that's pi over 2 plus pi over 2, which is 2 pi over 2. So that's pi. Okay, that's just showing you that every time pi goes by, you're going to cycle through the key parts of the tangent. Okay, all right, now just some observations. There is no minimum y value on a tangent. There is not a maximum y value if you look at the graph we did. The range is all real numbers, so the tangent will always give you every single y value. There's no breaks, so that would just be negative infinity to infinity. Or if you wrote this in set builder, you would say set of y, and you'd just say y is any real number. Okay, you can abbreviate it like that if you want to. Okay, the period is pi. The amplitude is you don't have one because there is no maximum and there's no min. Okay, you can only have an amplitude if there's a max or min. Okay, and the reason behind that is the definition of the amplitude is 1/2 the distance between the maximum and the minimum. So if you don't have one, then you can't construct that, use that formula. Okay, let's write down where we're undefined and try to make some predictions on this. So one thing that we see on here is -1 pi over 2. I like to put the 1 in front of that. And then +1 pi over 2. But if you go back to the unit circle, the god of trigonometry, it'll tell you where the next one is. So it just kind of goes like this if you think about this. You got pi over 2, y over 0 is undefined. But if we did another lap around the circle on this, okay, or just did, what did I just, sometimes I pressed the wrong button on this. Well, then I would go to 3 pi over 2. If I go to 3 pi over 2, you're still undefined. Okay, so if you kind of do this, you'll begin to see a pattern on this. Oh, come on, change colors. Hang on. Okay, OneNote drives me crazy. You'll hear me say that once every video. Okay, so it's 3 pi over 2. Now, predictably, what happens next is 5 pi over 2. All right, so the pattern on this is it's going 1 pi, 3 pi, 5 pi, so it's going odd pi. All right, so that's kind of every place where the tangent's going to be undefined is it's going to be odd pi over 2. All right, so the domain we would say like this. You would have to write this in set builder and say set of x such that x is not equal to k pi over 2, where k is an odd integer. Okay, just look for that pattern when you do that then. The vertical asymptotes are where you're undefined, so it would be same thing. They occur at 1 pi over 2, 3 pi over 2, and so forth. It's just odd pi over 2 forever. Right, so we would say the vertical asymptote equations would be x equals k pi over 2, and we would say k is an odd integer. Okay, so those are the basic features of a tangent. You want to understand what we did on the unit circle to get those points, how the asymptotes work, what the period is, that's pi, and then how to get the asymptotes in the equations. You can also use this formula, which is a little bit different than it was for secant or cosecant. What I can have students do generally is pick an asymptote. I don't really care what asymptote you pick. I prefer you start with 0 or a positive asymptote. Then it's just the period k. So remember the cosecant and the secant was 1/2 the period k. And the reason is because there's an asymptote halfway in the middle of the period. If you look at a tangent, there's not an asymptote in the middle of the period. There's what we call an inflection point there. So it's just basically you start with an asymptote, add the period, keep adding the period. That's where you get the next asymptotes. So it's helpful if you understand this. So one thing that you could do on this is you could also use this formula. You could say x equals, and if you look at the first asymptote we had, that was pi over 2. So you could say pi over 2 plus the period, which is pi, k, where k is an integer. Okay, so you could use that formula too. That's okay, that's okay. It's just you add the period k to get what that asymptote is. All right, so that will kind of take you through the tangent and what it looks like. We're going to go ahead on the next page and look at the cotangent and develop that with a very similar strategy. So what you want to remember on a cotangent is the cotangent is x over y. So what we're going to do is just kind of go around the unit circle. Let's start with 0. And if you do x over y at 0, you get 1 over 0, so you are undefined. So you have a vertical asymptote at 0 on a cotangent. If you go to pi over 4, then you just do x over y. That's easy to do in your head. Root 2 over 2 over itself is going to give you a value of 1. If you go to pi over 2, x over y is 0 over 1, so that's 0. Go to 3 pi over 2, you have negative root 2 over 2 over positive root 2 over 2, so that's negative 1. Then finally, if you go to pi, x over y would be back to an asymptote, so it's undefined. So this would define one period of the cotangent from 0 to pi. If you went out and did these things using the same logic, if you did negative pi over 4, you would be at negative 1. Negative pi over 2, you would be at 0. Negative 3 pi over 2, you would be at positive 1. And then negative pi, you would have a value of negative 1 over 0 again, so it's undefined. So you can see how these things repeat from undefined 1, 0, negative 1. Undefined 1, 0, negative 1, undefined. So it goes like that over and over again. Okay, so let's go ahead and put our graph together. So go ahead and take the time to get your x-axis put together. And make sure that you label everything, with the radian measure like we're used to doing. Okay, for the y values, go up to 4, like we did on the last problem. And go down to negative 4 like that. Okay, so you want to get everything kind of put together. And then I'd recommend that you go ahead and locate your asymptotes. Okay, so we have an asymptote at negative pi, so you want to put one there. Okay, we have another vertical asymptote at x equals 0. So that's really just the y-axis. Okay, so the y-axis is an asymptote, and then you have another one at pi. So those are your vertical asymptotes. And we'll end up finding an equation for those like we've been doing anyway. Okay, so let's see. Let's go start at negative 3 pi over 4. At negative 3 pi over 4, you have a y value of 1. At negative pi over 2, you have a y value of 0. Negative pi over 4, you have negative 1. So it's going to look similar to the tangent, but it's going to go more like this. Again, it approaches the asymptotes the way we would expect. And same thing here, pi over 4, 1, pi over 2, 0, 3 pi over 4, negative 1. And then go ahead and sketch in your graph like that. Okay, so that's how that graph goes for a cotangent. So if you compare the previous page and the tangent, it just kind of looks like this. Okay, so notice the tangent went this way, and the points kind of went asymptote, negative 1, 0, 1, asymptote. Okay, the cotangent is backwards. It's asymptote 1, 0, negative 1, undefined. And it's kind of a phase shift and a reflection if you think about that then. Okay, so let's do some observations. Minimum y value, there is not one. Okay, and there's no maximum. What you're going to find is the only trig functions that have max and mins are going to be the sine and the cosine. The other 4 trig functions have asymptotes, so they're going to go to infinity and negative infinity. The range is all real numbers. Y can be anything on a cotangent or a tangent. So we would say on that set of y is a real number. Or you could, interval notation, just say negative infinity to infinity. The period's pi. That's pretty evident from our graph. That would be 1 period right there, from 0 to pi. Your key points are asymptote, 1, 0, -1, asymptote. And I'm talking about y values, so it's real helpful to think of it this way. Vertical asymptote, y value 1, y value 0, y value -1, vertical asymptote. That's how the cotangent goes. And then the tangent is, you can think of vertical asymptote, -1, 0, 1, vertical asymptote. That's kind of helpful to memorize that when we start doing the graphs with transformations. Okay, the amplitude, what do you think? Is there a max and min? No, so we don't have an amplitude. Let's write down where we're undefined. The cotangent is undefined at -1 pi, 0 pi, 1 pi. And if you looked at your unit circle to kind of figure this out, what you're going to find is you're going to find this basically. The pattern's going to go like this. The places where x over y gives you undefined is right here. So if you just think of multiple laps around the circle, you would be at 0, 2 pi, 4 pi, and so forth. So it would just go pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, and so forth. All right? So basically, what's happening on this then is you're just getting integer pi's. So the domain, we would say set of x is not equal to, and again, you would have to write a formula, but these are integers. They're not odd or even or anything. They are integers. So what we would have is, we would just say k pi, and we would say k is an integer. You can use that abbreviation if you want to like that, so that would be your domain. Okay, the vertical asymptotes, same thing. Vertical asymptotes occur at integer pi's, okay, including, the negatives. You also have going that way. So we would say x is k pi, where k is an integer. Okay, so that would be how you would write the equations of those. Okay, just look for a pattern like we did on the secant and cosecant. Okay, all right, so that would be it. You can also use this formula. Notice on this we had a 0 was a vertical asymptote. So if you wanted to use this formula, you could say x equals 0, or you could use the first positive asymptote. The period is pi times k, and then if you do it this way, k is an integer. So if you use the formula, you would just say x equals pi k. K is an integer. Well, look at that. It's the same thing we got there. Okay, so that's the idea. All right, so that's your basic tangent and cotangent graph. When we get into transformations, I tend to teach this in an entirely different way than I teach the other trig functions. This is just kind of what I've come up with as a good technique. Okay, so I'm going to talk through on this part C kind of what you do if you're graphing a secant or cosecant. I always say start with finding a vertical asymptote. And what you do, if it's a tangent, you set the argument to pi over 2. The argument is the part that's in parentheses. So in other words, if you had something like the tangent, say, of 2x minus pi, the argument is this part right here. So if you want to find a vertical asymptote, you just set that equal to pi over 2. And the reason you do that is because the tangent is undefined at pi over 2. Okay, so I got this unit circle, and notice that at pi over 2, 1 over 0 is undefined, so the tangent's undefined at pi over 2. Okay? If it's a cotangent, if you're doing a cotangent, you set the argument equal to 0. So, for example, if you had the cotangent of 2x plus pi over 2, the argument is this thing. So to find where an asymptote is, you would set that argument equal to 0. And the reason you do that is because what happens on a cotangent is x over y. So notice 1 over 0 is undefined. So the cotangent's undefined at 0. The tangent's undefined at pi over 2. You don't have to memorize that. The unit circle will help lead you to the discovery of that if you forget it. Okay, then what I recommend you do is find a second asymptote. And what you do is just add the period, or you can subtract the period to get on the other side of that. So once you figure out the period, you get your first asymptote from step 1, then you get another asymptote by step 2, then it's pretty easy to figure out the rest. Okay, after you figure out the period, you want to get the increment by dividing the period by 4 like we've been doing. Then you plot the 3 basic points in between the asymptotes. And remember, the tangent in order, the key y values go, and it's always vertical asymptote, -1, 0, 1, vertical asymptote. But if it's a cotangent, it goes vertical asymptote, 1, 0, -1, vertical asymptote. So if you memorize that, then you got it made, okay? And then you got to do the transformations. The transformations generally are going to be the y values being transformed. Like if you have, in this example, a 2 and a -1, you figure those things in a simple arithmetic problem. Okay, so let's go down to this example. I'll do an example of each and maybe let you do one of these and see how you do with this. Okay, so a totally different approach. You actually don't have to worry about a factored form or anything on this. So what we're going to start with is we're going to find a vertical asymptote. You look at the thing that we call the argument. So since it's a tangent, we're going to set that argument equal to pi over 2 because the tangent's undefined at pi over 2. So you're going to solve an equation. So you want to go ahead and write down 1/2 x equals pi over 2. Then you want to solve that equation for x. Okay, well, the easy way to solve this equation is multiply both sides by 2. That will isolate x and get x by itself, so you would end up having x equals, notice the 2's cross out, so you would have x equals pi would be where one of the vertical asymptotes is found. So we found an asymptote, okay? It's not a bad idea to check as you do this. If you just look at tangent of 1/2 x, don't worry about, the 2 and -1. If you plug that in, you get tangent of 1/2 pi. Well, that's tangent of pi over 2, and you're undefined at pi over 2. You can check it. Once you get an asymptote, you can plug it in and see if it indeed gives you an asymptote, and it doesn't take very long to do that. Okay. Next thing we want to do is we want to find the period, really. So the period is pi over b. It's not 2 pi over b. It's different for a tangent and cotangent. So what that would be is it would be pi divided by 1/2. B is 1/2 in this problem. So that's pi times 2. So it's equal to 2 pi. Okay, so we get the period. Then you're going to use that to find adjacent asymptotes. That's the asymptote after pi. So what I'm going to do is I'm going to go like this. I'm going to go pi plus 2 pi, and then I'm going to go pi minus 2 pi to get my other asymptotes. So this would just be 3 pi, and that would be -pi. So what I'm doing, I'm going to graph over 2 periods on this. If I say graph on 1 period, you just need to get the one to the right or the one to the left of your original asymptote. So that's what we get is we have asymptotes at pi, -pi, and 3 pi. Okay, and you can already see the pattern of it. It's going to go 1 pi, 3 pi, 5 pi, 7 pi, 9 pi, etc. So it's going to go by odd pi values. Okay, the increment, we're going to do period over 4. Okay, the period is 2 pi. That's what we got. So you do 2 pi over 4. Reduce that fraction, you get pi over 2. Okay, like that. So every pi over 2 is where we're going to have key points to graph out this asymptote, graph out the function. Okay, well, let's just write these out. So I'd just start at 0, pi over 2, just start counting by pi over 2. So you'd have 2 pi over 2, which is pi, 3 pi over 2, then you'd have 4 pi over 2, which is 2 pi, and so forth. And you could continue to go to 3 pi because you have another asymptote. So then you would go 5 pi over 2, and then 6 pi over 2 would give 3 pi. Then you could go this way and get negative pi over 2, negative pi, and so forth like that. So what I'm doing is I'm counting by that numerator always, and I start at 0. You always want to start at 0 because that's the origin of the graph. Okay, so what we have so far is, these are the key things we did. We set the argument to pi over 2 to get that first asymptote. So we know we have an asymptote there, and then we found the period to be 2 pi. We added the period, subtracted the period to get 2 adjacent asymptotes, found the increment by dividing the period by 4. Now we know how to count out our x-axis, okay? All right, so I'm going to go to the next page. I need to probably zoom on this out on this a little bit so we can get this put together then, okay? So what I'll have you do is let's go ahead and just get our x values put together. What we're essentially going to do on this is just count these values out like we did on the previous, the last part of that problem. So let's just go pi over 2, pi, 3 pi over 2, 2 pi, and we're going to go all the way to 3 pi because we know we have an asymptote there. Okay, and we go to 3 pi. Then we're going to go backwards. So we go negative pi over 2, then we'll go negative pi. Okay, now those are the places that our asymptotes showed up, was there. So those are where our asymptotes are. And notice if you count to 5, 1, 2, 3, 4, 5, you have an asymptote. If you wanted to go further, you'd go 1, 2, 3, 4, 5, and you'd have another asymptote and so forth. Okay, so I'm going to go ahead and just sketch in the vertical asymptotes through these places. And then the y-axis, we can scale that maybe like up to 4 or 5, or probably 4 is probably a good choice on this basic graph like that. Okay, so we got everything set up. And let's get the y value set up, maybe going up to 4 and down to negative 4 like that. Okay, now let me go up and let me get the function we're working with and make a little quick. Okay, so like magic, there is the function that we're working with. Just, so we can refer to it and you can see how I'm getting the rest of these points. Okay, so here's what you want to remember. On a tangent, just remember it goes like this. And I'm talking about y values. You have a vertical asymptote, y value of -1, y value of 0, y value of 1, vertical asymptote. We already know where the vertical asymptotes are. So this is what you're going to do. Okay, you're going to start with -1 and you're going to figure in these other two numbers. Okay, that's a stretch shrink. That is a down 1. So what we're going to do is 2 times -1 minus 1. Then we're going to do 2 times 0 minus 1. And then 2 times 1 minus 1. Okay, this is going to give you -2 minus 1, or -3. This will give you 0 minus 1, or -1. Then this will give 2 minus 1, or 1. One thing I want you to notice on this, and this is kind of a cool connection to make, those things are 2 units apart. That's the meaning and the significance of that 2. Okay, you can kind of tell what's going to happen on that then. So basically, here's what you do then. When you're getting your graph constructed, okay, let's just start here. This point right here, it's going to go like this. You're going to have a y value of -3. So that point goes down -3. The next one has a y value of -1. and then the next one has a y value of 1. So I'm getting the values in between the asymptotes, and then you sketch it. The rest of it is a nice sketch, and then you got it. Okay, same thing over here. This first point would have a y value down -3. Middle point, y value of -1. Last point, like that. Okay, you have a very accurate sketch of a tangent now through 2 periods. Okay, that's it. Okay, it's not hard to do this if you do it this way. So the other thing we'll do, of course, is we'll check some points, and we'll look at the vertical asymptotes and their equations, and do that to finish up. Okay, let's just check a few points. It's up to you what you want to check. I'm going to start with, for checking, I'm going to use x equals, let's start at pi, and then let's maybe check the next one, 3 pi over 2. Okay, so I'm going to kind of zoom on this just a little bit. We're just plugging into that function. So what we'll have is y equals 2 tangent of 1/2 pi minus 1. Okay, well, the key thing is on this one is this is undefined. The tangent of pi over 2 is undefined, so we expect to get an asymptote at pi, and we do. So that proves that you have an asymptote there. Now I'll move to 3 pi over 2, so I'll have y equals 2 tangent of 1/2 times 3 pi over 2 minus 1. Okay, well, that ends up giving you 2 tangent of 3 pi over 4 minus 1. If you look on the unit circle at 3 pi over 4, what you end up getting is you end up getting the tangent of 3 pi over 4 is -1. So you get 2 times -1 minus 1, so you get -3. I want you to notice, too, when I checked, that's the same thing I did right there. Okay? So you're just verifying your arithmetic you already did. Okay? So we've got a correct y value of -3, and then you can check other points if you want to, okay, if you don't feel confident, okay? Okay, so moving down, next thing is the domain. So if you look at where we're undefined at -1 pi, 1 pi, 3 pi. So what do you predict comes after 3 pi? 1 pi, 3 pi, 5 pi, 7 pi. What you have is odd pi. Okay? All right? And I'm not talking about a dessert there. I'm not talking about apple pie. So it's odd pi that we have there. Okay, so here's what we'd say. We'd say set of x such that x is not equal to k pi, and we'd have to say k is an odd integer. That's how you would state the domain, which is different than the asymptotes. Well, the equation of the asymptotes is almost the same thing. It's just x equals k pi, and again, k is an odd integer. Okay, so that's how that gets put together. All right. Okay, so pause on this if you need to kind of go through this a little bit. I'm going to do cotangent next, so I'm going to go ahead and move to the next page and help you with a cotangent, okay, which is very similar. Okay, so on this one, I'm going to go up and grab my unit circle real quick, just for reference on this. Okay, so the first thing we're going to do is just kind of figure out the asymptotes and do this. Now again, you don't have to worry about a factored form. It doesn't make any difference. The phase shift and everything's going to be figured into your calculations. Okay. Now if I want you to find the phase shift, yeah, then you would want to go ahead and factor that out. I'm going to go ahead and do this on this. Just kind of as we get our final answer, you can kind of see how the phase shift affected this. So I'm going to take a pi out. Okay, like that, and then remember to figure out what goes there, you need to take the pi over 4 and divide it by the pi that you took out. So that would be pi over 4 times 1 over pi. So that would give 1/4. Okay, and it's okay if you get a number. That kind of makes it work kind of simple without worrying about pi. It's just fractional values. Okay, so anyway, we're going to be phase shifting, but you don't really have to worry about that. You just got to worry about finding a vertical asymptote. So what you do on a cotangent is you take the argument. To me, it's just as easy to take the non-factored form, and you set it equal to a place where the cotangent's undefined. The cotangent's undefined here because x over y, in this case, is undefined. 1 over 0 is undefined, so you set that equal to 0. So that's why you do that. Okay, if we can solve this equation effectively for x, then we have our first asymptote. So I'm just going to move the pi over 4, so I get pi x equals negative pi over 4. I can either divide by pi. To me, it's just as easy to multiply by 1 over pi on this. Okay, that way x gets by itself, so you would end up with x equals negative 1/4. And that has a lot to do with where our phase shift is. Okay, so that is vertical asymptote number 1. Okay, so we have that. Okay, so again, set the argument to 0 on a cotangent, and then if you do that correctly, you know where your first asymptote is. Okay, step 2, we want to find the period. The period is pi over b on a tangent or cotangent, so be careful about that. Okay, b is pi, so you just have pi over pi, so it's equal to 1. Okay, so what we end up doing to get other asymptotes is we just do this. We take the asymptote we found, and we just add the period to it, or we subtract the period to it. We're going to get 2 adjacent vertical asymptotes. Okay, we'd have to get a common denominator. So I'm going to multiply that by 4 over 4. So I'd end up getting negative 1/4 minus 4/4. So that's negative 5/4. Okay, so that is one of our asymptotes right there. Okay, do the same thing over here. Common denominator. So you'll get negative 1/4 plus 4 over 4. So that gives 3 over 4. All right, so those are our asymptotes right there. When we graph, we just need to show that we have a vertical asymptote at those 3 numbers. And there's a pattern there. I'm seeing negative 1, 3, negative 5. There's a pattern to that, but if you don't see that, you can use that formula. Okay, so we got the asymptotes. That's how you want to start a tangent or cotangent. How do you find the increment? Period over 4, exactly. The period in here was 1, so you'd have 1/4. So we're just going to start counting out this increment starting with 0. So 1 over 4, count by the numerator, 2/4 is a half, then 3/4, see you're at an asymptote. So that's a good stopping point because that gives you an asymptote. Go backwards, it'd be negative 1/2, or I'm sorry, negative 1/4, because the increment's 1/4. Then it would be, that's probably good enough for 1 period. I'm going to keep going with this. Then it's negative 1/2. Then it's negative 3/4. Then negative 4/4 is negative 1. And then you'd end up to negative 5 over 4. Okay? Write it down if you have to before you reduce the fractions. I'm just going 1/4, 2/4, 3/4. And this way I'm going negative 1/4, negative 2/4, negative 3/4, negative 4/4, negative 5/4, and reducing the fractions in my head. Okay. All right, so let's plot this out and get everything set up and label everything. So we'll start with, on this side, 1/4, 1/2, 3/4. That's good enough, okay, because we have an asymptote at 3/4. We go this way, we'll have negative 1/4, negative 1/2, negative 3/4, negative 1, negative 5/4. Okay, our asymptotes, if you look at kind of what we had there, we had asymptotes in these locations. We had an asymptote at negative 5/4, negative 1/4, and 3/4. And I want you to notice, if you count to 5, what happens? It's just 1, 2, 3, 4, 5. You have an asymptote. Go this way, 1, 2, 3, 4, 5, you have another asymptote. So we're getting the 5 key points that we need here. Okay. All right, so what I would do next is just get your asymptotes. So you have a vertical asymptote through negative 5/4. You have one at negative 1/4. Then you have another one at positive 3/4 like that. Okay, now we're doing a cotangent. So I would also just probably take this up. Let me get a screenshot of the factored form here, or just kind of write it down at the side. I think what we had is y equals 1/2 cotangent. And let's see, we can either do the factored form or the non-factored form. I'm going to write the factored form that we have. And then what we're going to do is just start transforming points. Okay, so this is what you want to know. I'll do the y-axis thing here in a minute. So what you got to remember on a cotangent is it goes vertical asymptote, then it's backwards. 1, 0, -1 vertical asymptote. That's how those y values go inside of the asymptote. What's going to change that is the number 1/2 and +2. That's going to shrink the y values and move them up 2. So I'm going to calculate those things just one at a time. So I do 1/2 times 1 plus 2. Then I do 1/2 times 0 plus 2. Then I do 1/2 times -1 plus 2. Okay, so it's always kind of the same. You can get all this done in kind of one step. So this is going to be 1/2 plus 2. That's 2.5. Or if you prefer, 2.5. The next one is 0 plus 2. So that's equal to 2. And then the next one is -1/2 plus 2, which is 1.5. Or if you prefer, 1.5. Now I want you to make the connection on this. These things are 1/2 apart. So is that. So these things should be logical to you. These things are off by 1/2, and then we moved everything up 2. So those are the key values. So this is what you're going to do then to get your final graph is this. So your first point, which is after that asymptote, is going to go up 2.5. So let's just kind of get this put together like that. 1, 2, and then 2.5 or something like that. Actually, I think I'll do it more like this so I have a little bit more room. So let's say that's 1, 2, 3, 4, like we've been doing, and then you can just kind of estimate the halfway points like that. Okay, so the first point has a y value of 2.5. So if you go to the right of your asymptote, that first point's up 2.5. Okay, the second point is up 2, so that would be at the 1/4. The third value is at 1.5. Okay, that's enough to sketch in your graph, just showing how it connects to the asymptotes. Okay, same thing happens over here. Start at the asymptote. Your first point has a y value of 2.5. Second one has a y value of 2. Third one at 1.5. Then you got how your graph goes. That is a beautiful, a terrible graph. I went too far. Okay, it's got to go before the asymptote here. Okay, so it's like this. Okay, it should never cross the asymptote. It just approaches it. Okay, so that's what your graph would look like. You can check a couple of points if you want to, the way I've been showing you. If I were starting this problem, I would start at checking -1/4. Then I would probably check 0 and see if it works the way it's supposed to. But I'm not going to show that on this particular problem. Okay, so that's it. The next thing is let's give the domain of the function. Okay, so let's just write down all the places where we were undefined. So we were undefined at -5/4, -1/4, and 3/4. Okay, now our period on this was, let's see, the period was 1. So I'll kind of talk about what you can do on this to get this domain and vertical asymptotes put together. Well, if the period is 1, Then after 3/4, you would just add 4/4 to it to get 7/4. And then if you did 7/4 plus 4/4, you would get 11/4. Now it's kind of hard to see a pattern. These things are going up 4 every time. You can see that they're going up 4. So then the next one would be 15/4 and so forth. But it's kind of hard. If you look at those numbers, 3, 7, 11, and 15, it's every other odd. I really wouldn't want you to say it that way. I'd probably just prefer that you use the formula. So the formula goes like this. X equals a vertical asymptote plus the period k, where k is an integer. So what you would do on this, you can just write the formula like this. We have a asymptote at 3/4. You can use any of these asymptotes. I just like to use the smallest positive one. So you would just say 3/4 plus the period, which is 1, times k, where k is an integer. And that will be a guaranteed equation of asymptotes. So I just write the answer as x equals 3/4 plus k. X is any integer. That's the formula you can use that can bypass having to find a pattern. Okay? The domain would just be set of x. X is everything except where there's an asymptote. So you'd say x is not equal to 3/4 plus k, where k is an integer. Okay, you don't have a pi in there because of the way the increment worked out. Okay, so that's how that would go. One thing that you can always do on this too is, if you're not sure, notice that k is an integer. So if you added an integer 1 to this, you would get 3/4 plus 4/4, which would give you 7/4. And that would give the next asymptote. That's all it is. You're just, if you add an integer to 3/4, you're going to get the rest of these asymptotes. Okay, that's the idea. Okay, so carrying on, let's see. I think with this one, I'm going to have you do the problem that follows. And just one problem. I'm not going to take the time to have you do more. You're going to do that on your homework and stuff. Let's just try a tangent and give it your best shot and see how you do. So you can go ahead and pause and come back and check my work on that. Okay, well, let's check and see how we did here. Now, with this one, you want to see that you had your asymptotes that would, if you did what I've been showing, you would have 5 pi, pi, and 9 pi. The period would be 4 pi, and the increment one would be pi. And then I'm going to go over that in just a minute, and then we'll go to the next page, and you can check your graph. So it doesn't really matter that you do a factored form on this. It's not really necessary. But what the key thing is, you want to take the argument and set it to pi over 2, because the tangent's undefined at pi over 2. And when you do that, if you solve this equation, you want to make sure you solve this equation okay. I basically just moved the 3 pi over 4 to this side, got a common denominator. So I got 5 pi over 4 and multiplied both sides by 4 to get 5 pi. Okay, the period is pi over b. B is 1/4 in this problem. So you're doing pi divided by 1/4. Therefore, you get 4 pi. Okay, then to get your adjacent asymptotes, you take the first asymptote, 5 pi, add the period to get 9 pi, subtract the period to get pi. Okay, and you can go further back to the left or whatever. I just usually like to get an asymptote to the right and an asymptote to the left. Okay, and then since your increment is the period 4 pi over 4, that means your x-axis is just going to go by pi's. Okay, pause if you need to, otherwise I'm going to go to the next page. So here's what your graph should have looked like. So let me kind of talk through some of the things we have here. We have, again, I set up my increment by pi. I made my graph go from -5 to 5. And then the key thing to remember is, since you're doing a tangent, you have an asymptote, then the y values go like this. Asymptote, -1, 0, 1, asymptote. Okay, so it goes like this. So I do the negative and then the -3. These are the two numbers that are transforming those final y values. So I do -1 minus 3 to get -2, -0 minus 3 to get -3, and then -1 minus 3 to get -4. So then it's just plot these values. So The first point to the right of an asymptote has a y value of -2, then -3, then -4. So you got your sketch. Okay, we know where our asymptotes are. That's how you transform the y values. Okay, if you want to look at how I checked these things, you can. I checked the point pi and 2 pi. They both turned out to be correct. You can look over what I did there. And then the last thing I did is I used the formula because the asymptotes are kind of hard to see a pattern on. The asymptotes actually on this go pi, 5 pi, how was it? 5 pi and then 9 pi. And what they're doing is they're going up 4. So it's kind of hard to find a really good logical equation for that. Then it would go 13 pi and 17 pi and forever just going up 4 pi, going up what the period is. So it's just as easy to use the formula, which is take a vertical asymptote plus the period k. So the first asymptote that we got, the smallest one was pi. Then I add the period 4 pi k, then I got it. Okay? That is easy to do in your head. If k is 1, then you have pi plus 4 pi times 1, so you get an asymptote at 5 pi. Okay? If you do k is equal to 2, you get pi plus 4 pi times 2, which is 9 pi. So see, it's matching those things. So you can check your formula that you get and see if it's working out. Okay? And then the domain is just the same thing. You just say x is not equal to pi plus 4 pi k. K is an integer. Okay, so that's how I would recommend you learn how to do tangent and cotangent, is by following those, the strategy of finding asymptotes to begin with. And the key thing to not forget is the tangent has this structure. It's vertical asymptote, and then the y values in the middle go like that. If it's a cotangent, it's kind of backwards. It's a vertical asymptote, then the y values go like that. If you remember that, that will easily help you get those values in the middle. All right, so that will wrap this section up. There's nothing else. It's all about graphing tangent, cotangent, secant, and cosecant. Hopefully this helps you to get solid on how to do the graphing and to understand how the functions graphs work.